Welcome back to Ghost Alpha FPS Framework series. In part 1, we planned the framework. In part 2, we built the project foundation. We created the folder structure, naming standards, coding conventions, project architecture, and the overall direction of Ghost Alpha. Today, we're finally starting to build the gameplay foundation. This is where Ghost Alpha starts becoming a real FPS framework. We're going to create the shared language for the project, define the core gameplay architecture, build the player framework, create the attachment system, and establish the data-driven structure that the rest of the framework will depend on. This isn't the flashy part of development, but it is one of the most important because good architecture now prevents painful rewrites later. Every FPS project starts out clean. A weapon class here, player class here, maybe an inventory system, maybe some attachments. But 6 months later, everything is connected to everything. Changing one system breaks 3 others. Adding a new weapon means touching 5 different classes, and the project becomes harder to work on every single day. Today, we're preventing that future. In part 3 of the Ghost Alpha FPS Framework series, we're building the gameplay foundation that everything else will depend on. Before we start coding, make sure you're using the Ghost Alpha Part 2 project as your starting point. I've included a link in the video description where you can download the completed Part 2 project. That project already contains the folder structure, naming standards, project setup, and architecture we've built so far. Once you've downloaded it, extract the project somewhere convenient. Once you've extracted it, you may need to generate the project files before opening the C++ solution. To do that, right-click the ghostalpha.uproject file and choose Generate Visual Studio Project Files. If you're using Rider, you can still generate the project files from the U project or open the Unreal project first and let Rider create the solution from here. After the project files are generated, open the .sln file in Visual Studio or Rider. Then do a full compile before making any Part 3 changes. This makes sure your local copy of Part 2 base project is clean and ready before we start adding the gameplay foundation. If you're following along with your own project, that's perfectly fine too, but make sure you've completed the Part 2 setup first, because everything we build today assumes that that foundation already exists. Now, let's start building the gameplay framework. The first thing we're doing is creating a shared language for the framework. One of the biggest mistakes I see in gameplay projects is every system inventing its own terminology. One system calls it primary weapon, another system calls it active weapon, another one uses an integer. Eventually, nobody knows what anything means, so Ghost Alpha centralizes these definitions using the ghost_alpha.h. This becomes the common language for our framework. One major addition to Ghost Alpha is the use of a dedicated finite state machine, or FSM. And throughout this project, FSM is always the abbreviation I will use for finite state machine. We create separate state systems for different responsibilities. Weapon FSM controls weapon behavior. ADS FSM controls aiming transactions. Move FSM controls movement states. Stance FSM controls player stance. Game FSM controls the overall gameplay lifecycle. Keeping these systems separate prevents state logic from becoming a tangled mess. Weapon state controls the weapon lifecycle. This allows us to know exactly what the weapon is doing at any point in time. ADS state is kept separate because aiming is not the same thing as firing. A player can be aiming while idle, a player can be aiming while firing. The player can stop aiming while the weapon is reloading. These are different systems. Movement states aren't just movement speed. Each state may require different weapon offsets, camera positioning, sway, bob, animations and restrictions, and that's why we define them now. Movement and stance are separate concepts. A player can be crouching and moving, prone and stationary, standing and sprinting. Keeping these independent gives us more flexibility. The player's game FSM controls the player's gameplay lifecycle. This is where we define states like pre-game, respawning, spectating, and post-game. We've also added a dying state. That gives us support later for systems like revives, bleed out timers, player recovery before transitioning to fully dead. While we're in here creating enums, let's create the enums we will need for the attachment data. We define a broad category first, which is the attachment type. Then each attachment category gets its own specific subtype enum. So for optics, we will have an optic type, magazines a magazine type, muzzles a muzzle type, underbarrel attachments underbarrel type, stocks and stock type, flashlights a flashlight type, and ammunition and ammo type. Before we build the weapon class, we will need a way to represent attachments that are attached on the weapon. We're going to create a shared structure called fWeaponAttachment. This structure represents a weapon attachment instance and contains the information needed to mount that attachment onto a weapon mesh. There will be a different structure used for available attachments, which will be in the weapon data class, and this will include a setting for the rank for that attachment. This gives us a clean separation. The attachment type tells the framework what category the attachment belongs to. The subtype tells the specialized child class what specific kind of attachment it is. So an optic attachment can be a red dot, holographic sight, ACOG, scope, thermal, optic, or night vision. A magazine type can be a box magazine, extended magazine, drum magazine, double magazine. A muzzle attachment can be a flash ender, compensator, muzzle brake, or suppressor. And ammo can represent bullet types, rockets, fuel-based ammunition for weapons like flamethrowers. This structure keeps the framework organized without creating one giant generic attachment class full of unrelated data. In this series, we are moving towards a fully data-driven architecture. Characters define available weapon slots. Weapon slots define available weapons. Weapons define available attachments. And all of it can be controlled through ranking restrictions. This means we can build progression systems, class systems, and loadout systems without constantly changing code. The attachment system being used in Ghost Alpha defines separate attachment categories from attachment subtypes. For example, an attachment type of an optic as an optic type of a red dot, or an attachment type of magazine as a magazine type of drum magazine. This keeps the system extremely scalable. For the attachment data, the base attachment class will be abstract. It cannot be used directly. Designers should always create one of the specialized child attachment types. This prevents invalid assets from being created. Each child class automatically sets its own architecture type in the constructor. The weapon data owns the socket mapping for each available attachment. Instead of putting socket names inside the attachment data, each weapon defines its own list of available attachments. Each entry in the list contains 4 key variables: the attachment data, the socket name for this weapon mesh, transform for the rotation, scale, and position offset when attaching to the weapon, and the required rank. The same red dot optic can be used across multiple weapons, but each weapon can decide where that optic attaches. This means that the attachments can be reusable across multiple weapons. The weapon controls the placement. This also works better for rank restrictions. A weapon can allow an attachment at one rank, while another weapon may unlock that same attachment later. So the relationship between weapon data owns the available attachment list. Weapon data defines the attachment itself, and the available attachment rules connects them all together. Now, let me show you this whole approach using attachment data with my own loadout footage. The important thing here is that the UI is not inventing the rules. The weapon data is driving the rules. It knows this weapon requires a magazine and ammo. It knows which attachments are available. It knows which socket each attachment uses. It knows the transform offset and alignment. And it knows the rank requirements. So when the loadout screen shows available optics, magazines, ammo, or locked attachments, that information is coming directly from the data-driven attachment rules. Now, let's walk through the attachment data code. The important thing to understand is that the GA attachment data is the base class for all attachment data assets. This class is abstract, so we cannot create a generic attachment data asset directly from it. That is intentional. We don't want somebody creating a generic attachment and then manually selecting whether it's an optic, magazine, muzzle, flashlight, or ammo type. Instead, we want designers to create one of the correct child classes. So the base classes only contain information that every attachment has in common. Notice what is not in this class. There is no weapon socket name. The attachment does not decide where it mounts. The weapon data decides that. This keeps attachment data reusable across different weapons. A red dot sight can be used on the same attachment data asset, but one rifle might mount it to one socket and another might mount it to a different socket, and a pistol might use a different socket completely. The attachment data describes what the attachment is. The weapon data describes how the attachment works on a specific weapon. The constructor sets the attachment type to none by default. Since this class is abstract, this default value is mostly a safety fallback. The child classes will set the real attachment type individually. Now, we create the derived attachment data classes. Each child class has one simple responsibility. It defines its attachment category and then adds only the data needed for that category. For optics, we derive from the GA attachment data. The optic class stores an E-optic type. That means this asset can represent iron sights, red dot, holographic sight, ACOG sights, scope, thermal optics, or night vision optics. Then in the CPP file we have the constructor. The magazine attachment class works the same way. It stores its own subtype enum of e-magazine type. Now, the magazine attachment can be a box magazine, extended magazine, drum magazine, or double magazine without changing the base classes. Then, in the CPP file, we have the constructor. So the muzzle, underbarrel, and stock attachments follow the exact same pattern. Each class owns the subtype enum that belongs to the attachment category. Again, this pattern is simple. The base class owns the common data. The child class owns the specific subtype. The constructor, in all cases, sets the broad attachment category. Laser attachments are slightly different. We are not creating a laser subtype enum. Instead, the laser uses an F linear color. That gives us more flexibility than hard coding enum values. So, if you want red, green, blue, infrared, or any custom laser color and alpha setting, the data asset can be controlled directly. Flashlights also use their own subtype enum. Later on, we will expand this class with intensity, attenuation radius, cone handles, shadow settings, and volumetric fog behavior. Then in the CPP file we have the constructor. Finally, ammo attachments use eAmmo type. This allows us to support standard ammunition, armor-piercing rounds, hollow point rounds, incendiary rounds, tracer rounds, rockets, and fuel for weapons like flamethrowers, plus many more. Then in the CPP file we have the constructor. So the final rule is simple. Attachment data describes what the attachment is. Derived data describes the specific category and subtype. Weapon data describes whether the attachment is allowed on a weapon and what socket it uses and what rank is required. This separation gives us a reusable attachment system without locking socket placements into the attachment itself. Now we're going to build the player framework. Player base is the shared low-level framework class. It is abstract and is not blueprintable. All player-controlled blueprints come from the player or from the NPC player. This keeps inheritance clean and predictable. The same rule will apply to weapons. Weapon base is an abstract class and should never be used directly by any blueprints. Rather than creating one giant player class, we're separating gameplay responsibilities into dedicated components. Health handles life and death. Stamina handles sprinting and recovery. Armor handles damage reduction. Inventory handles loadouts and weapons. Combat handles weapon interaction. Movement handles movement rules. Team handles faction and team relationships. Ranking handles progression and unlocks. Notice that we're not putting gameplay logic directly inside the player. Health doesn't need to know about inventory. Inventory doesn't need to know about ranking. Ranking doesn't need to know about movement. Each system has a single responsibility. The result is a cleaner and more maintainable architecture. Now, let's walk through the GA player base class, because this is one of the core player framework classes. The goal of this class is to own the shared player systems that both real players and NPC players need. It is the foundation, but it is not the final blueprint parent. Player blueprints will come from the GA player class, and NPC blueprints will come from the GA_NPC player class. First, we give the player base a reference to character data. Character data will eventually define things like allowed weapon slots, character restrictions, loadout rules, and other character-specific settings. This keeps the character configuration data-driven instead of hard-coded directly into the player class. It also allows one player class to manage multiple options for different characters. Next, we add the core gameplay components. Health handles life, damage, healing, and death. Stamina handles sprinting, recovery, and exertion. Armor handles protection and damage reduction. Inventory handles weapons, loadouts, attachments, and ammo. Combat handles current weapon interaction. Movement handles Ghost Alpha movement rules. Team handles team and faction logic. Ranking handles experience, progress, unlocks, and rewards. The important point is that we are not putting all of this directly into the player class. The player owns the components. The components own the specific gameplay responsibilities. Then we add the player finite state machines. The move FSM tracks movement states like idle, walk, running, sprinting, jumping, falling, and so on. The stance FSM tracks standing, crouching, prone, and sliding. The game FSM tracks gameplay lifecycle states like loading, pre-game, spawn wait, protected, playing, dying, dead, respawning, spectating, and so on. These are separate on purpose. Movement, stance, and gameplay life cycles are different concerns. Keeping them separate makes animation, movement, camera behavior, and gameplay rules much easier to manage later. The player also keeps a reference to the current weapon, but notice that this class does not do. It does not contain the firing logic itself. It does not decide how the weapon reloads. It does not control ADS behavior. The weapon owns the weapon behavior. The player simply routes the input to that current weapon. These functions become clean input entry points. When the player presses fire, start fire is called. When the player releases fire, stop fire is called. When the player aims, start ADS is called. When the player stops aiming, stop ADS is called. When the player reloads, reload weapon is called. But each function simply passes the request to the weapon. This is the key idea. The player receives the input. The weapon handles the weapon logic. That keeps the player class clean. It also means we can swap weapons without rewriting input code. The player does not need to know if the current weapon is a rifle, pistol, shotgun, launcher, or even a melee weapon. It just sends the request to the current weapon. In the constructor, we create each player component using the create default subobject. This gives every player instance the same core framework systems: health, stamina, armor, inventory, combat, movement, team, and ranking. You'll also notice I'm already creating these three state machine components: move FSM, stance FSM, and game FSM. Right now I'm simply establishing the ownership. The player owns movement state, the player owns stance state, and the player owns the game state. We're not building the state machine itself just yet. That comes in part 4. For now, we're just wiring the framework together so the ownership is already in place when we implement the actual FSM systems later. So, GA player base is not a gameplay dumping ground. It is the framework owner for the shared player systems. It owns the components, it owns the state machine, it tracks the current weapon, and it routes input to the current system. That is what keeps the player framework clean as Ghost Alpha grows. Now let's walk through the GA weapon-based class. This is the shared foundation for every weapon in Ghost Alpha. The goal here is not to build all of the firing, reloading, recoil, animation, and projectile logic yet. The goal is to define what every weapon needs to own. The first thing to notice is that the weapon-based class is abstract and not blueprintable. That means we do not create weapon blueprints directly from this class. This is a low-level framework class. Later, specific weapons C++ classes can be derived from this, and those classes can become the proper blueprint parents. The first major property is weapon data. Weapon data defines the configuration for this weapon. That includes available attachments, required attachment types, socket names, transfer offset rules, ammo rules, and ranking requirements. The weapon class owns the runtime behavior. The weapon data owns the configuration. This is where our attachment design becomes useful. The attachment data describes what the attachment is. The weapon data decides whether the attachment is allowed on this weapon, which socket it uses, how it is aligned, and what rank is required to use that attachment. This means the same optic, magazine, muzzle, laser, flashlight can be used across multiple weapons. Next, we create two state machine components, one for weapon behavior and one for ADS behavior. FSM stands for finite state machine. The weapon FSM will control states like equipping, idle, firing, reloading, unequipping, and disabled. The ADS FSM will control aim states like not aiming, entering ADS, and exiting ADS. In this part, we're wiring the components into the weapon. The deeper state machine behavior will be the focus of the next state machine section. In the constructor, we create both FSM components. This establishes ownership. The weapon owns its weapon FSM. The weapon owns its ADS FSM. The player does not control those internal weapon states directly. Player simply sends requests like fire, reload, or aim. The weapon decides what to do with those requests. The weapon also stores runtime ammo. Current ammo is what is currently loaded into the weapon, and reserve ammo is what the player has available for reloads. These values belong to the weapon instance because they change during gameplay. The weapon also stores the current equipped attachments. We use the shared F weapon attachment struct here. The struct contains the attachment data, the socket name, and the transform offset. Because this is an array, the weapon can support multiple attachments at the same time. For example, optic, magazine, muzzle, underbarrel, flash, laser, and ammo. Finally, the weapon base exposes the core weapon actions: start fire, start ADS, and stop ADS, and reload. These are clean entry points that the player or combat system can call. The player does not need to know whether the current weapon is a rifle, pistol, shotgun, launcher, flamethrower, or melee weapon. It simply sends the request to the weapon. So, this is the weapon-based foundation. Weapon data controls configuration. The weapon owns its weapon FSM and ADS FSM. Runtime, ammo, and attachments live on the weapon instance. The public weapon functions provide a consistent interface to the rest of the framework. This keeps weapon behavior inside the weapon system instead of spreading it across the player inventory, UI, and combat code. Next, we prepare the player state. Player state contains data that belongs to the player rather than the current pawn. This means information can persist throughout death and respawning. Examples include kills, deaths, team assignment, faction, and later ranking, experience, and progression. Player state becomes the persistent representation of the player throughout the match. Another goal of Ghost Alpha is keeping gameplay systems data-driven. Difficulty data can eventually control things like health, stamina, armor, fall damage, AI behavior, damage scaling, and ranking rewards. Because we've separated systems into components, these values can be configured without constantly modifying gameplay code. As we end this video, you should now perform a full compile from Visual Studio or Rider. This part needs to compile cleanly before moving on. In part 4, we're going to focus heavily on state machine system and start turning these framework pieces into actual gameplay logic. We'll build a generic FSM component, define how states are registered, entered, updated, and exited, and then integrate that system into both the player and the weapon frameworks. If you'd like a head start, check out my Ghost Alpha State Machine Snippet video, where I break down the FSM architecture in more detail. That video will give you a jump start before we begin part 4. If you're finding this series useful, please consider subscribing. My goal is to continue releasing Ghost Alpha FPS framework videos, code snippets, and deep dives into professional FPS architecture. Subscribing, liking the video, and leaving comments genuinely helps the channel grow and allows me to keep investing time into building and sharing this framework with the FPS development community. Thanks for watching, and I'll see you in part 4.